Gas chromatography is an analytical technique that is used to identify the number of components that are present in a mixture, as well as the relative ratio of the components that are present. It can also be used to identify components, assuming you have appropriate standards for comparison. So we'll talk a little bit about what's going on with gas chromatography. This is a simple schematic of what's present. We start with an injection port. So your sample is injected into that port. It is kept quite hot. So your sample will vaporize as soon as it gets into that port. We are constantly pushing a carrier gas through that port, commonly helium, although we are using hydrogen in ours, but the carrier gas will basically blow or carry the sample that is now vaporized into a gas from the injection port into a column. The column is essentially just a long hollow tube. It is usually coated with some oil or wax, which is referred to as our stationary phase. The stationary phase is usually some silicon-based oil or wax that's coating that interior of the column. Standard column lengths right now for analytical columns is around 30 meters or 100 feet in length. And the diameter is typically a third or a quarter of a millimeter in diameter. And the coating inside that column is typically on the order of micrometers in thickness. The column is inside of an oven, so the column itself is kept fairly warm, not hot, but warm enough or hot enough that we keep the sample that was now blown into the column near the boiling point. We don't want it to all vaporize, because if everything that's in it vaporizes, it will be carried through with the carrier gas. By having it a bit cooler, we can actually get some separation. I'll talk about the basis for that shortly. But eventually it comes out and it goes through a detector, which will detect the amount of material that goes through, but it does not give identity of the analytes in the sample. We have what is called a flame ionization detector. Basically, the sample is burned, and the ions that are created during that combustion conduct some current, and we can use that to determine the relative amounts of material that's coming through. So what we are measuring is first retention time. The retention time is basically a measure of the time from injection to detection, the time it spends in the column. And that will depend in part on the sample itself. There are two factors that affect retention time. One of them, as I mentioned, is this vapor-liquid equilibrium. The sample is vaporized in the injection port, but then once it gets into the column, it is constantly equilibrating between liquid and vapor, meaning that the sample will spend part of its time as a vapor. It goes in, it will condense to a liquid. But then that liquid will re-vaporize, and as long as it is in the vapor state, it will travel through that column. So we basically have a vapor that's coming in, travels, and then it sits there. Then it will vaporize, travel some more, and condense and sit there. Then vaporize, travel some more, condense, and sit. Basically, the boiling point will control how long it spends as a vapor and how long it spends as a liquid. A component with a higher boiling point will spend more time as a liquid, and therefore it travels through that column more slowly, whereas a component with a lower boiling point will spend more time as a vapor and will travel through the column more quickly, and that causes separation of the components. So the volatility is one factor that affects retention time. And of course, we can equate volatility with the boiling point. There is a second factor I mentioned there is a stationary phase coating that column, and you do have interaction between the stationary phase and the analyte. If you have strong intermolecular forces, that will also slow the compound down. If we compare something like ethanol, so this is common drinking alcohol, has a boiling point of around 80 degrees Celsius. And then there's a second component, toluene, has a boiling point of around 111 degrees Celsius. Based on the first factor, what we would expect is that the ethanol would come out first, followed by toluene, since ethanol is more volatile. Depending on the stationary phase, though, we could see that change. For example, one stationary phase, called a carbowax column, has a lot of OH groups hanging off that stationary phase. So we would have hydrogen bonding between the ethanol and that carbowax coating. And since that is a strong intermolecular force, that would slow down the movement of the ethanol. You can think of it as having Velcro on the bottom of your shoes and trying to walk across carpet. It would slow you down because of its strong interaction. And in fact, if we have a carbowax column, toluene will typically elute before the ethanol, even though toluene is less volatile. The columns that we have in the GCs that we typically use, and the ones that we used for your unknowns, in fact, the ones we will be using for all of the samples in the organic labs, are nonpolar stationary phase. And so boiling point will be the predominant factor that affects the separation. This is a sample chromatogram. This is one that has many different components, and as you can see, we've got a bunch of peaks. They're different sizes. Above the peak is a number, that is the retention time. If you note on the x-axis here, time is given in minutes. So this peak eluted at 4.75 minutes. This peak eluted at 5.4 minutes. And so those are our retention times. Usually, in addition to this, you will get a report that comes with it, similar to the one down here, where the peaks are identified, the retention times. This is what the RT stands for, retention time. For example, if this peak at 4.18 minutes, there is a second column that's important, and that is the area percent. This gives relative amounts. So of that mixture, 5.23% of that mixture is the material that eluted at 4.18 minutes. If we go down a couple peaks, we had another peak, retention time 5.4 minutes. It represented 1.9%. So it was a minor component. And that's indicated by the fact that we actually have a fairly small peak. Of course, peak size is not just the height of the peak, but also the width. So note the peak at 4.18, even though it's a relatively short peak, it is also a broad peak, so it represents 5%. It's a larger percentage than the peak at 5.4, even though they are of similar heights. Now, your chromatogram, since you distilled the material, and it should be pure, a single component, it should be a single peak. Now, we are trying to use this to identify compounds. So what we want to do is look at the retention time and then compare that to standards. So if you go on to As You Learn, you will find instructor information. I have uploaded standards. So if we come here, we can see unknown GCs. We click on that little arrow and expands it, and we can see a list of the various chromatograms that are posted, as well as standards for two of my sections. So we have a chromatogram here. To identify what compound this is, we could look at the retention time, either here, or if that's a little hard to read because of the overlap with the peak, we can come down below. And we see a retention time of 1.599 minutes. And the units are here as well as there. To identify what this compound is, we would look at the standards. So we would then go to the appropriate standards for our section, and we would look at the retention times of the various compounds. Note here that we have the identity of this component. This is 1-hexene. It's also at the very top of the page, but this has a retention time of 1.4, not 1.599 or 1.6 minutes. So this is not a good match. We scroll to the next one, the 1-chlorobutane. You can look at the retention times here, 1.49, so we're still quite a bit off, 1.49 minutes. Scroll to the next one, the pentanal, and again it's also on the chromatogram itself. Here we have a retention time of 1.606 minutes. 1.606 versus what we had here, 1.599. These are, for all intents and purposes, the same number. We're off here by a few thousandths of a minute. So that would be a fraction of a second. So these retention times are the same, which tells us that our chromatogram here is pentanal because it matches that retention time. If we continue to look down, 1.7 minutes and 1.76 minutes, we can see a chromatogram here of a mixture of all five, and we can see there that they are well separated. But this is how you identify an unknown using the gas chromatography. You look at the retention time from your chromatogram of your unknown, then you go to the standards and compare them and find the one that matches. And again, the match should be within a few thousandths of a minute or within less than a second, basically.